You can use the Nernst equation to calculate cell potentials. Here we need to calculate the cell potential for a zinc-copper cell where the concentration of zinc 2 plus ions and the concentration of copper 2 plus ions in solution is 1 molar, and we're at 25 degrees C. So we're talking about standard conditions here. Just to remind you of the reduction half reaction and the oxidation half reaction, copper 2 plus ions are reduced. They gain electrons to form solid copper. And solid zinc is oxidized, so zinc loses 2 electrons to form zinc 2 plus ions. Those 2 electrons, right, the electrons lost by zinc are the same electrons gained by copper 2 plus, so they cancel out when you write your overall reaction. So down here we have our overall redox reaction. And the standard cell potential is equal to positive 1.10 volts. So you just add the standard reduction potential and the standard oxidation potential. So all of this we've covered in earlier videos. And now we're going to see how to calculate the cell potential using the Nernst equation. So let's go ahead and write down the Nernst equation, which is the cell potential is equal to the standard cell potential, E0, minus 0.0592 volts over N times the log of Q. So this is the form of the Nernst equation. This is one of the forms that we can use when our temperature is 25 degrees C. So let's think about what these things mean in the Nernst equation. So the standard cell potential, E0, right, we've already found that. That's 1.10 volts. So this 1.10 would get plugged in to here in the Nernst equation. N is the number of moles that are transferred, number of moles of electrons that are transferred in our redox reaction, and that's 2, right? 2 moles of electrons are transferred, so N is equal to 2. Q is the reaction quotient. So Q is the reaction quotient. And Q has the same form as K, which are using non-equilibrium concentrations. So think about writing an equilibrium expression. So to write Q, think about an equilibrium expression where you have your concentration of products over the concentration of your reactants, and you leave out pure solids. So we're going to leave out solid copper, and we have concentration of zinc 2 plus, so concentration of our product. Over the concentration of our reactants, we're going to leave out the solid zinc, so we have the concentration of copper 2 plus. All right, we know what those concentrations are. They were given to us in the problem. The concentration of zinc 2 plus is 1 molar. Concentration of copper 2 plus is 1 molar. So we have 1 over 1. So the reaction quotient for this example is equal to 1. So let's go ahead and plug in everything. All right, so we have the cell potential E is equal to the standard cell potential. That was 1.10 volts. Right, minus 0.0592 over N, where N is the number of moles of electrons, that's equal to 2, times the log of the reaction quotient. Well, log of 1, right, our reaction quotient for this example is equal to 1. Log of 1 is equal to 0. So we have the cell potential is equal to 1.10, right, minus 0. So the cell potential is equal to 1.10 volts. So we know the cell potential is equal to the standard cell potential, right, which is equal to 1.10 volts, positive 1.10 volts. So this makes sense, right, because E0, right, the standard cell potential, let me go ahead and highlight that up here. The standard cell potential, E0, is the voltage under standard conditions. And that's what we have here. We have standard conditions. Our concentrations are 1 molar, right? We're at 25 degrees C. We're dealing with pure zinc and pure copper. So this makes sense, right? The Nernst equation should give us that the cell potential is equal to the standard cell potential. Let's find the cell potential again for our zinc-copper cell, but this time the concentration of zinc 2 plus ions is 10 molar, and we'll keep the concentration of copper 2 plus ions the same, 1 molar. So if we're trying to find the cell potential, we can use our Nernst equation, right? So the cell potential E is equal to the standard cell potential, E0, minus 0.0592 volts over N times the log of Q, where Q is the reaction quotient. Let's plug in everything we know. We know the standard cell potential is positive 1.10 volts, so we have 1.10 volts. We're trying to find the cell potential E. So E is equal to 1.10 minus 0.0592 over N. So N is the number of moles of electrons that are transferred. So that was 2 electrons. So N is equal to 2, so we plug that in here, times the log of Q. And from the previous example, remember Q, the reaction quotient, is the concentration of zinc 2+, right? Concentration of zinc 2+ over the concentration of copper 2+. So concentration of products over reactants, right? Ignoring your pure solids. So for this example, the concentration of zinc 2+ ions in solution is 10 molar, right? So that's 10 molar over copper 2+ is 1 molar, so 10 over 1. So Q is equal to 10 for this example. So now let's find the cell potential. So the cell potential is E. So E is equal to 1.10 minus. You can actually do all of this in your head. So 0.0592. Let's say that's 0.060. So this is 0.060 divided by 2, which is 0.030. So we have 0.030. Log of 10 is just equal to 1. So this is 0.030 times 1. So 1.10 minus 0.030 is equal to 1.07. So the cell potential is equal to 1.07 volts. I like to think about this as the instantaneous cell potential. So when your concentrations are 10 molar for zinc 2+ and 1 molar for copper 2+, 1.07 volts is your instantaneous cell potential. What happens to the cell potential as the reaction progresses? Well, let's think about that. Let's go back up here to our overall reaction. All right, what happens as we make more and more of our products? Well, the concentration of zinc 2+ ions should increase, and we're losing our reactants here, so the concentration of copper 2+ should decrease. So what happens to Q, right? If we're increasing the concentration of zinc 2+ and decreasing the concentration of copper 2+, Q should increase. And what does that do to the cell potential, right? So in the Nernst equation, if we're increasing Q, what does that do to E? Well, let's go ahead and let's just plug in a number. Let's just say that Q is equal to 100. So let's say that your Q is equal to 100. Let's plug that into the Nernst equation. Let's see what happens to the cell potential. So E is equal to E0, which we'll go ahead and plug in 1.10 there. So 1.10 minus 0.0592 over 2 times log of 100. So now we're saying that Q is equal to 100. So we have more of our products as the reaction progresses. So what is the cell potential? E is equal to 1.10. Log of 100 is equal to 2. So log of 100 is equal to 2. That cancels out this 2 here. So we have 1 minus 0.0592. 1 minus 0.0592. I'll just say that's equal to 0.060 just to make things easier. So 1.10 minus 0.060 is equal to 1.04. So the cell potential is equal to 1.04 volts. So notice what happened to the cell potential, right? So we increased, let me change colors here, we increased Q. We went from Q is equal to 10 to Q is equal to 100. What happened to the cell potential? The cell potential went from 1.07 volts to 1.04 volts. So as the reaction progresses, right, Q increases and the instantaneous cell potential, E, decreases. So Q increases and E decreases. So what happens at equilibrium? What is the cell potential at equilibrium? So what is the cell potential at equilibrium? If you remember the equation that relates delta G to the cell potential, so we talked about this one, delta G is equal to negative NFE. And from thermodynamics, right, at equilibrium, delta G is equal to 0. So if delta G is equal to 0 at equilibrium, what is the cell potential at equilibrium? E must be equal to 0. So the cell potential is equal to 0 at equilibrium. So let's think about that. So if the cell potential is equal to 0 at equilibrium, let's write down our Nernst equation. So the Nernst equation is E is equal to E0 minus 0.0592 over N times the log of Q. Well, at equilibrium, E is equal to 0. So we plug that in. So we have 0 is equal to the standard cell potential, E0, minus 0.0592 over N, times the log of Q. But at equilibrium, remember, Q is equal to K. So we can plug in K here. So now we have the log of K. And notice that this is the equation we talked about in an earlier video. The standard cell potential E0 is equal to 0.0592 over N times the log of K. So just an interesting way to think about the Nernst equation. So the Nernst equation is very useful for calculating cell potentials, right, when you have different concentrations.